Chapter 9.2, Finite Mathematical Systems. So in this chapter we're going to be taking the mathematical systems we explored last time and making them basically smaller and a little bit more abstract. So we'll start with some numbers in a way that we would understand. So, definition. A finite mathematical system is one whose set contains a finite number of elements. So finite, remember, means just a set number. So I can count the number of elements and then stop at some point. I can say there's 5 or 10 or 100 elements and then I stop. So, for example, a system that we should kind of understand is one called clock arithmetic, or clock 12 arithmetic more specifically. So the clock 12 arithmetic is formed from the numbers on a clock and how they interact with each other. So the elements of the set are the numbers 1 through 12 because those are the numbers on a clock. The operation that we'll use is addition in a clockwise manner. So we know that when we go around a clock, at a certain point we pass 12, noon or midnight, and come back, start over at 1, 2, 3, 4, and go around again and again and again. So, for example, if I add 4 plus 9, I'm really adding 4 o'clock plus 9 hours to get to 1 o'clock, as opposed to 4 plus 9 being 13. Or 9 plus 4 is 9 o'clock plus 4 hours, which gets me again to 1 o'clock, instead of it being 13. So we have over here an image of the, basically the arithmetic table for clock 12 arithmetic. So 1 plus 1 is 2, 1 plus 2 is 3. We get this sort of thing, but where things start to get a little bit different is anytime we're going over 12. So, for example, if I add 11 o'clock plus 2 hours, I'm going to get to 1 o'clock. If I add 11 o'clock plus 3 hours, I get to 2 o'clock. Plus 4 is 3. Plus 5 hours is 4, and so on, right? So we get this sort of new area of the table where instead of this line here being 13, it's now 1, and then 2, and then 3, and 4, and 5, and 6, and so on again until we get to 12 a second time. So 12 plus 12 is like saying noon plus 12 hours gets us to midnight, right? We're back at 12 again. So all of this should be something we can visualize on the clock. We'll be able to picture other clock arithmetic tables that aren't just 12 hours as well. But let's explore this by asking the question, is this a group? So now that we understand what a group is, we know that we need 4 specific axioms for it to match, and for it to be a commutative group specifically, we have the 5th axiom of commutativity. So first, is it closed? So closure means that when I add 2 numbers within this set, do I always get another element of the set, or do I sometimes exit the set entirely? Well, in this case, we can see when we have a finite system, we can often just draw the whole table and we can visually see every possible addition that can occur. We can't do this with infinite systems because the table would be infinitely large. So, if I add any 2 numbers on here, we can just look at the body of this table and see every number on here is the numbers 1 through 12. So no matter what, when I add the numbers 1 through 12 to 1 through 12 within the clock 12 arithmetic system, I stay within that system. So we do in fact have closure. Next, we want to find what is the identity. So the identity is the element where when I add it, I sort of come back to where I started, okay? So if we think about a clock again, how many hours do I need to add before I'm back at the same time? And you may first think, well, 24 hours before I'm back at the same time of day, but on the clock itself, if it is, 4 o'clock, how many hours until it's 4 o'clock again? AM versus PM. So it's 4 AM, how many hours until 4 PM? well, that's 12 hours away, right? And so even though 4 a.m. and 4 p.m. we understand are two different times, on the clock they appear to be the same. They're both 4s. So when I add 12 hours, I get back to where I started on the clock. So 12 is our identity, and we can visually see this within the table because, so this row represents our set, right? And here, when I add 12, it's just a direct copy of that row, right? Everything is a direct copy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And similarly, going in the other direction, we have direct copy of that first column. So that's what you're generally doing when you're looking for the identity, when you have a finite system and a whole table to visualize it. You want to look for which element gives me a copy of the header row or header column. Should be the same element in both directions. So 12 both ways gives me that copy of the header row and first column. So 12 is the additive identity, as opposed to our usual 0, but we don't have 0 in this case, we have 12 instead. Okay, next we want to check, does every element have an inverse? So remember, inverse means so I have some element, I add another element to it to get back to the identity. So no matter what, if I name any time on the clock, can I get back to 12? 12 being the identity. And of course I can. I'm not just going to skip over 12 o'clock for some time. Like if it's 3 o'clock, oh, I'll never get back to 12. That wouldn't make any sense, right? So every element has some way to get to 12, and we can visually see this because a 12 appears in every row. So 11 plus 1 hour, 10 plus 2 hours, 9 plus 3 hours, 8 plus 4 hours, and so on and so on. No matter what time I start at, I can always get back to 12. Okay? Now we want to check associativity. Associativity is a little bit harder because we need to be able to show that associativity holds no matter what. And so we're going to talk a little bit about how to shortcut this, but in this case, I'm just going to show an example of it working, and note that this is still just addition. Yes, it's addition with a little bit of changes to it, but addition is an associative operation. Like, I haven't changed the operation here. It's still just adding in the typical way. We're just kind of going around a clock instead of going to 13, 14, 15, and so on. But it's still addition. So associativity is going to hold because it holds for addition. And I can show an example of it holding here, like so. So remember, associativity means that if I add two numbers and then add a third number, it's the same thing as adding the second and third number first, and then adding the first number. So 2 plus 6 is 8, and 8 plus 8 is 16, but again, we want to think about on our clock, if I'm at 2, I add 6 hours, I'm now at 8. I add 8 more hours, so I go 1, 2, 3, 4, 5, 6, 7, 8. I'm at 4 at the end, versus adding 6 plus 8, so I start at 6. I add 8 hours, 1, 2, 3, 4, 5, 6, 7, 8. I'm at 2, and then add 2, so 2 plus 2, 2 more hours, I get 4. So either way, I get to 4. So this is a demonstration of the associativity. It does not prove it's always associative, but in this case, we're allowed to assume because we are allowed to assume this about addition. Similarly, for commutativity, in the past I said we could assume that for addition, but when we have a finite system, we can actually visually see commutativity fairly easily. So commutativity holds for addition, in general, but there's also a way to see it. So notice that, for example, 3 plus 7 is 3 o'clock plus 7 hours is 10 o'clock. 7 plus 3 would be 7 o'clock plus 3 hours is 10 o'clock. They're the same, but visually we can sort of see this pattern that's going to occur. If I sort of draw this diagonal line and pretend you can see the rest of it, there's this symmetry to these points, right? There's this symmetry across this diagonal line. So we're going to learn that that is one way to recognize commutativity, is through a symmetry across this diagonal. So in fact, we have all 5 of our axioms, so we are not just a group, but a commutative group. And so as I said, when we have a commutative group, here's a visualization of that diagonal. So a few notes. If not every element in the set appears in every row and column of the table, that's when you need to check the associative property. So if we look through here, we can see 1 through 12 appears in every row, so most likely associativity will hold. This is not necessarily the case, but it is a lot, like that's when you have to be very careful. So if you ever notice a row that's missing something, then you should check associativity using that missing number, and we'll see that later. If the elements are symmetric over the main diagonal, which is what we call this diagonal line I drew before, then the system is commutative. So you can see that commutativity. And it is possible to have groups that are not commutative. These are called non-commutative or non-abelian groups. However, a non-commutative group must have at least 6 distinct elements. So we have 12 elements here, so it is possible it could be non-commutative, but we're going to look at much smaller finite systems in the future. So with those smaller systems, if it's a group, it's going to be commutative. But once we get up to 6 elements, there is a way to have a group that's not commutative. This is entirely possible, even if that's like a sort of weird concept to think about, since in general, that's most of the things you've worked with in the past have been commutative. Okay, so let's look at another example. So here, I have a finite system that's much more abstract. So we want to know, is this a commutative group? So we will determine whether this system, which uses the set ABC, so that's our set, and the operation triangle. So this triangle is just like the plus sign here, right? This plus, which you can't really see, this plus tells me that my operation is addition. But in this case, my operation is something abstract. I don't need to understand what triangle means because I have a whole table that was given to me that's going to tell me how to form this possible group, but at least this finite system. So we start by asking, is it closed? To answer the is it closed question, we just look in this area, okay? So we want to compare this area to the set. Again, this being the set, which should match this. This is also the set. These should match. If you've done it correctly, they always match, okay? So we want to know, does anything appear here, anything here that isn't in the set? And in fact, everything there is A, B, or C, right? There's no D in there. So A, B, C, that's all that's in there, we're good. So this is closed. If you ever see something that isn't A, B, or C, that means it's not closed. That isn't in the set, at least. Next, we look for the identity. Once again, remember the identity is the element that when I add it or multiply it, or in this case triangle it, I get back to where I started, essentially. So we want to visually see this in our finite system by looking for the row and column that is a direct copy of the header and first column. So in this case, here's my header. Which row is a direct copy of it? That would be this one, right? And here's my first column. Which column is a direct copy of it? It's the first column. And so which letter signifies this column? The letter is A, right? Because that's A's row and A's column. So A is our identity. Next, does every element have an inverse? So an inverse is something that gets us back to the identity. So in other words, we just want to see, can I always find A in every row and every column? So I look for A in the first row, here it is. First row, here it is. Second row, third row, right? First column, second column, third column, it's all there. So no matter what, I can get to A. And then we always want to list what is the inverse of, what is the inverse of what? We don't want to just say, yes, everything has an inverse. We want to prove that everything has an inverse, and we can do that in this case by identifying the inverse of A is A, which should always be true for the identity. The inverse to the identity is always the identity. But the inverse to B is C, because B triangle C is A, and C triangle B is also A. So B and C are inverses of each other, which is how that should work if you've done it correctly. Next, we check for associativity. So remember that I said, for associativity, we want to look for any situation where there is a row or a column that is missing an element, because that's usually when you might run into problems with associativity. So in this case, we can kind of notice that, well, this column has no B, this row has no C, this column has no C, this row has no B. There's a lot of issues, right? So we're going to pick one of those. So for example, I picked B doesn't appear in row 3. So we definitely need to check associative property, and I'm going to check it using B's. Again, generally you just want to start being suspicious at this point, and you check until you've either checked every possible combination, or you find an issue. So in this case, we can pick any ones we want, right? But we definitely want to include, I definitely want to think about B, because B is the missing one in that row, and somehow getting to that row, so maybe combining B and C. There's more than one way to go about this. Again, you just want to kind of pick some things at random, but try not to use the identity. We want to use B's and C's, because we know the identity interacts well. The identity row and column has everything, but the B row and B column and C row and C column are missing elements, so those are the ones we want to focus on. So I'm going to pick B, triangle C. So B, triangle B. Okay. Now I'm already kind of spoiling for us that this isn't going to work, but let's see how it works out. So B, triangle B means I'm taking B into B, right? So I'm here now. So that's where I got this. And now I triangle it with C. So I go B with C, so I get here to A. And so I finish there. Then, second, I'm going to start with B triangle C. So I start B with C, so I start with A. Then I'm going B triangle A right here. So I start at B, and I go to A right here, and whoop, that's a B. And so it's different. So it definitely matters what order you do this in, okay? So the left one I'm picking to be this column. The thing on the right will be the thing from the row. You want to make sure you're keeping that consistent throughout, or else it can also throw you off. All right, so we have broken associativity, which means this is not a group. We have our answer. No, this is not a group, so it can't be a commutative group, but just for the sake of completeness, I am going to make a note that the commutative property does in fact hold, because there is symmetry about the main diagonal. So if I draw this line here, we can see B across from B, C across from C, A across from A, right? We have this symmetry here. So it is commutative. It doesn't matter because we have already disproven it, but we do have commutativity. Alright, so we're going to finish this up by looking at some of the practice problems at the end of this, because I really want to address a few more examples here. So, in this case, I have 4 finite systems with 4 different abstract operations, and we want to figure out which ones are commutative groups. Now, every one of these is a system that has less than 6 elements in its set. We can see here that there are 4 elements in this set, 3 in this set, 3, 3. So no matter what, if it's a group, it's going to be commutative, but we can also visualize that as well. But let's go through our 5 axioms, right? So 1, is it closed? 2, is it, does it have an identity? 3, to have inverses. Does everything have an inverse? Not just, does one thing have an inverse? 4, does it have associativity? And then 5, is that commutativity? Right? So, again, remember that these 4 tell us if it's a group. The 5th one just says it's a special kind of group, a commutative group. So, first, we want to say, are these all closed? Okay, so we're going to look through, and we're going to notice, again, the elements of the set. So the elements of this set are 2, 4, 6, 8. Do we see anything in here that isn't 2, 4, 6, or 8? No, we're good there, right? So let's just, 2, 3, 4. I'm going to make a little chart. We can sort of picture this, right? So this first one, we're good. We got closure. Here, our set is x, y, z. And do we see anything besides x, y, and z? Yep, there's a t. That's a problem. We're not closed. So automatically, that's not a group, and we can really just stop. We figure out this is not a group. So it clearly can't be a commutative group. Next, e, omega, and lambda, maybe? A fancy L. Do we see anything besides those in here? Nope. So that seems all good. Similarly, we got a dollar sign, a percent sign, and oh, that should be an @ sign. That's actually just a typo on my part. But anything in here? Nope. Dollar, @ and percent. That's all good, right? Okay. So next we go and look for the identities. So the identity, again, is which column is going to match that first column. So I look through and I find, okay, well, here's a 2, 4, 6, 8. Yep, found it. So my identity is 6. Here I got x, y, z. My identity is x. Again, well, that's a little bit, I'll make it a fancy x. Here's a fancy x. Again, this is already not a group, so it doesn't really matter whether certain things match, but just for the sake of thoroughness. Now, e omega lambda, that shows up right here. So that is, omega is my identity. Dollar sign, percent, and @ sign. So dollar, percent, we got dollar @ percent, but no dollar percent @. So this one fails. We don't have that. So this one, not a group. This one is not a group. Let's see. Let's keep going. Do we have inverses? Okay, so we want to know, can I always get back to 6? Okay, so 2 and 2 got back to 6. 4 and 8. And let's see, 6 and 6, of course. And 8 and 4, right? Yep. So we've got inverses. So inverses are 2 to 2 and 4 to 8. That's not 4 minus 8, it's just 4 to 8. Those are inverses of each other. Next, don't care about this column anymore because once it's not a group, it doesn't really matter that much about anything else, so I'm actually just going to ignore that. Similarly, if there's no identity, this column's not going to matter, so we can just put it away. But over here, let's look for our inverses. So E, how do I get to omega? I get E plus the L. So E to omega gets me, or E to lambda, sorry, that should be an L. E and lambda are inverses of each other, right? L and E, yep, together we get omega, so we're good. Associativity, again, we just want to look through these two remaining options and see, does every number show up in every row? Yeah, 6824, 8246, 2468, 4682. Every row, associativity is going to be fine. L, E, omega, L, omega, L, E. We're good on associativity. And finally, main diagonal. Do we have that, symmetry across the diagonal? We do, in fact, have that symmetry. We are commutative. And, yep, we've got the same symmetry. So, commutative. So we have yes, no, because of not closed, yes, no, because there's no identity. Finally, I want to talk about this clock arithmetic. We talked about clock 12 arithmetic, but we can talk about clock any number arithmetic, any positive number at least, because we can build a clock that's just a different size. So instead of being 12, I'm going to make one where 8 is the highest number. So I'll go 1, 2, 3, 4, 5, 6, 7, 8. And so 5 plus 7 means I start at 5 and I go around 7. So 1, 2, 3, 4, 5, 6, 7. So I end at 4. So that is 5 plus 7 is 4 in clock 8 arithmetic. So you may be asked to build a table for clock 8 arithmetic as well. So if we wanted to do that, we would kind of build that same kind of table we had for the clock 12. I'm not going to skip all the way back there, but essentially we'd have our plus, and we'd have 1, 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 4, 5, 6, 7, and 8, right? And when we add, we're all fine until we get up to that end of our clock. So here's 8. 1, 2, 3, 4, 5, 6, 7, right? So 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, 5, 6, 7, 8. But 1 plus 8, that's going to be, instead of 9, we'll be back to 1. Now 2 plus 1 is 3. 2 plus 2 is 4, 5, 6, 7, 8. And 2 plus 7, so that means 2, 7 hours past 2 is going to get me 1. 2 plus 8 is 8 hours past 2, which gets me back to 2. And we can sort of see this pattern that we're kind of just shifting over, right? 3, 5, 6, 7, 8, 1, 2, 3. 5, 6, 7, 8, 1, 2, 3, 4. Because we have what is called like a sort of cyclical relationship, because we make cycles around the clock. So 6, 7, 8, 1, 2, 3, 4, 5. It's getting a little bit small to write, but we can finish out the table in this way. And again, if you're ever unsure, you can just build the clock yourself to do any of this type of addition. So 5 plus 7, again, is we just start at 5, add 7 hours. Or you could start at 7 and add 5 hours, because it should be commutative. That's how clock arithmetic works, because it is just addition. It's just addition within this sort of specific situation that has these limitations because we're going around this cycle of the clock.